and why is SU2 and SO3 of specific importance, especially in physics. And then we're going to discuss reducer representations of those without using nearly algebras. Okay, so the motivation, as I'm a physicist, I try to give mostly physical motivation. So we're interested in Lie groups because whenever symmetries arise, we have a Lie group acting on our system. In classical mechanics, Lie group actions can lead to interesting things for mathematicians, like symplectic reduction in symplectic geometry, as usually classical system in classical mechanics is described as symplectic manifold. And then when you act with this Lie group on the manifold and you have a proper and free action and it's Hamiltonian, there are some specific constraints, but the upshot is that if some constraints are satisfied, then you can quotient out this action and obtain a symplectic manifold of lower dimension. And in particular, this happens for the harmonic oscillator, where we have a large group of symmetries. Another interesting problem is the Kepler problem, where you have SO3 symmetry as well. Yeah, so that's from the classical mechanics side, but in quantum mechanics, SU2 is of particular importance because spin appears there by representation theory of SU2. And moreover, I would like to make a remark for people who are interested in representation theory, although this is a bit advanced. The projective representations of SO3 correspond to the normal representations of SU2. And what you should think about projective representations is simply that it's a representation up to a phase. And in quantum mechanics, this appears from the fact that the wave function itself, the state, is defined up to a phase because the probability be conserved. In general relativity, we also have these Lie groups. They appear as the isometry groups of spacetime. So those transformations which leave the metric invariant. And in particular, these are generated by Killing vectors. And SO3 is, of course, here as well, for example, in the Schwarzschild solution or in famous solutions. In fact, these isometries and Killing vectors are a mathematical tool to generate solutions. So if we know symmetries of the solution, then we can guess the solution, or that's how we search solutions usually. In gauge theory, they appear as well. Maybe this is the most interesting part for mathematicians, because mathematicians, or rather geometers, are really interested in principal bundles. And moreover, in Riemannian geometry, you can classify spaces of constant curvature by Lie group actions. So SU2 in particular is interesting because it leads to Yang-Mills theories in physics. And roughly speaking, a principal bundle is a fiber bundle where the fiber is a Lie group, just roughly speaking. In quantum field theory, the Poincare invariance appears, which is, of course, as well, SO3 is a subgroup of that. So this is the motivation to study these. Now let's see what SU2 is. So it's a Lie group. It's basically a matrix Lie group, one of the classical groups. And it's the definition is given there. And moreover, we have that we can identify S3 with SU2. So we can identify it with the sphere by the map given there, and as we know that the sphere is compact, we obtain that SU2 is a compact Lie group. Okay, so now I want to move on to conjugacy classes. So we're interested in the conjugacy classes of SU2 because we want to classify the irreducible representations, and we know that the irreducible representations of SU2 are basically classified by the characters, but the characters, if we know the characters of the irreducible representations, we know everything. But the characters are constant on conjugacy classes, since are class functions, and then we're interested in these conjugacy classes. And then the conjugacy classes are given as here. This is rather clear geometrically, as but there's going to be a detailed proof in the handout if you're interested. And therefore, the class functions can be identified with 2 pi even periodic functions, because we see that if we change the parameter here by 2 pi, we get back to where we started from, and we see that a theta and a minus theta are conjugate to each other by the following matrix equation. So the upshot is that we have this conjugacy classes. Yes, is there any question? Okay. Okay, so now we go to reducer representations, and like one of them is the tree representation, which maps everything to 1. This is not so interesting, but there. Yeah, thanks. Okay, so there's also an obvious 2-dimensional representation. In physics, this is called the standard representation. And the character of this is just given by, we can compute the character only on the conjugacy classes, as we saw. And then using that, we get that this is, the character is 2 cos theta. But now if we want to go from this representation to higher dimensional ones, for example, one method is to do the tensor product representation. However, this is not going to be reducible, because the tensor product can be decomposed into the symmetric part and then anti-symmetric part. We will see moreover later that both of these are reducible, but if it decomposes as a direct sum of reducibles, this shows that this guy is not reducible. So far we have seen the representations, the reducer representations, which was a 1-dimensional one, a 2-dimensional one, and so we have these 3. And now this suggests that we could look at the n-symmetric power of C squared to find the reducibles. However, we know that the n-symmetric power of C squared is isomorphic to the space of complex homogeneous polynomials of degree n in 2 variables, which is a vector space by the virtue of pointwise multiplication and addition. And an element of this space is given here. And moreover, to show that they are isomorphic, we will give an isomorphism, which is not canonical as it depends on the basis, but we map basis to basis, and the isomorphism is basically this. So indeed, the space of complex homogeneous polynomials of degree n in 2 variables is isomorphic to the space of n-symmetric power of C squared. And now I claim that the representations of SU2 are given by these tuples, where we have a map and the vector space, and the map is given like this. So we take an element of SU2, this is A, and then we act on a polynomial and evaluate it in Z1 and Z2, and we define it like this. To actually see that this is indeed a representation, we would need to do some work, but I'm not going to show it because it's literally just algebra. So what you would need to show is that this is indeed a group homomorphism. That's what we would have to show. We would have to show that each pi n a is linear, and we would have to show that if we take a polynomial, if we take an element of Vn, we still get an element of Vn by acting on pi n a. This is going to be done in the handout if you're interested, but I think it's rather straightforward algebra to check it. Okay, so we come to the main part of the talk, where we say that these tuples, which we just defined here, this pi n Vn, these guys are the reducible representations of SU2. And this is the main theorem of the talk. And we can see this by the following arguments. So we know that SU2 is compact, as we have seen, because it's diffeomorphic to the tree sphere. And we know that compact Lie groups admit a finite Haar measure. And if they admit a finite Haar measure, this means that all their representations are unitarizable. So it is enough to show that each SU2 equivariant endomorphism is a multiple of the identity. This follows from the converse of Schur's lemma. So it's basically Schur's lemma what's coming here into play. And now we take an arbitrary element in SU2. We take an element of SU2, which is of this form, and we want to compute the action of the representation on the basis. And to this end, we just denote Fk evaluated in Z1, Z2 as Z1k, Z2n minus k, because this is a basis of the space Vn, which we just constructed before. And now we compute how this representation acts. So recall we had here pi mb of f in Z1, Z2 is f in A inverse Z1, Z2 transpose. So that's what we have here. Wait, so Kazali says that he can't see or hear anything in the call. Does anyone have this issue? Or can you guys hear me properly?
I can hear you and see you.
Okay. Then I think it's something on Kazali's hand. Okay, so here we compute the action, and this is just by the definition, and then we plug in what it means to be Fk of this guy. And this means simply that we take this guy to the power of k and this guy to the power of n minus k. That's what we have here. And after rearranging this equation, we get to the last part. And thus we can read off by taking, because Z1 and Z2 are arbitrary, we can read off that pi n of b applied to the basis is e to the I theta n minus 2k applied to the basis. But now we also know that A is equivariant, SU2 equivariant, because that's what we assumed. So we compute the action of on pi n of b on A of fk, and this must be equal to the action of A on pi n of b acting on fk. And here the action is basically just matrix multiplication. And to this end, we literally just have A applied to the guy we computed before, right? So we computed this guy before, but since this is just matrix multiplication and these are just numbers, or while we can say that A is a linear operator, we can just pull out these guys, and A will act on Z1k to Z2n minus k. But we can rewrite this fk, A acting on fk, Z1 evaluated Z2 by using this definition. So we can read off that pi n of b applied to AFK is e to the I theta n minus 2k AFK, where fk is the basis of Vn defined like this. Okay, so now we choose theta so that all the powers I to the theta n minus 2k are distinct. I'm sorry, there's a typo, so their n minus 2k should be above here, up. And now we pick an arbitrary element of the vector space Vn, which we constructed. And because every vector space admits a basis by the axiom of choice or by Zorn lemma, we can expand this V in the basis, right? And using this, we can compute the action of the representation on this given vector. And this goes by literally the same means which we just did before. So because each pi and b is linear, we can just pull in the sum and ck, and we will just act with this guy on fk. But recall that we know how this guy acts on fk from here, right? So we know how it acts because we computed it already. So just plugging it back in, we obtain that pi and b acting on the vector we chose is a sum from 0 to n of some coefficients times e to the I theta n minus 2k. So this shows that V is in the theta 2n minus 2kth eigenspace of the endomorphism pi and b. And this in particular shows that the coefficient is 0 for all L not in k. Therefore, we conclude that V is CK is a CKFK, but we also know that what we just derived, like from here, right? We derived this from here, and this implies that AFK is also in the IT tan minus 2k eigenspace. Therefore, AFK must be a multiple of FK. And now we want to find who this multiple is. I mean, who these CKs are. So if it would be that this CK is a multiple of the identity, then we in particular would be done. Okay, so to see that this CK is a multiple of the identity, to finish the proof by the converse of Schur's lemma, we take a rotation matrix, which is in particular in SU2. And this is a real rotation matrix. And once again, we compute the action of the representation on this rotation matrix and use equivariance of A. So it's literally the same computation we did before. So here in the first line, I just use how the representation acts on the rotation matrix. This is just the action of the representation. In the second line, I use that the form of Fn, which is the basis defined here, right? Here. So basically, I will get that this is to the power of n times this to the power of n minus n, which is 1. Therefore, I get only the first term. And now I use Newton's binomial theorem. Yes? Okay, if there's any question, feel free to stop me. So here I just use Newton's binomial theorem to expand this to the power of n into this sum. And then I use that A is linear, so I can pull these guys in, and A will act on the basis. But A acting on the basis is literally can be rewritten as A acting on Fk evaluating Z1, Z2 by simply recalling that Fk is the basis. And therefore, we conclude that using that AFK is CKFK, we conclude this last part. But now we can compute the action of the representation matrix on AFN, and this in particular should be equal to the action above by equivariance. SU2 equivariance means that it holds for all matrices in SU2, so in particular for rotation matrices as well. And this computation is very similar to what we did above. So here I just use the definition of representation. Here I use what it means for Fn to be basis. I mean, how Fn looks like. And here I just use Newton's binomial formula. And here I basically just regroup the terms, right? I just regroup the terms. But now we can rewrite this basis using the Fk which we had, and using the linearity, because these are just numbers, we can just pull this in. And because these two guys have to be equal by equivariance, we have that everything here is equal. So CK, so all of the CK must be a multiple of identity, right? So CK has to be equal to Cn for this to hold. And that basically shows that we are done. And the matrix A is a multiple identity as we desired, namely a Cn, a multiple of the identity. And moreover, by Schur's lemma, the converse of Schur's lemma, this finishes the proof that these guys are reducible. So we obtain the reducible representations of SU2. Now, it's a really fair and legit question to ask, are there more? I mean, I didn't say anything about the classification of the irreducibles. I only gave you some representations, and I told you they are irreducible, and I showed you. But in order to see that these are all the irreducible representations of SU2, we actually need some more work. So we need to do some work to see this. But before we get there, let us compute the characters of these reducible representations and how are these characters related to the Clebsch-Gordan decomposition. This is in particular, this is of particular interest to physics because the Clebsch-Gordan decomposition is basically the addition of angular momenta. Is there any question or? I think someone is echoing. Okay, all good. Yeah, so we also want to see that these characters are orthogonal because that's what it means to be reducible representation. So that would be just reformulation of the theorem we just proved. In fact, they are orthonormal. The characters of reducible representations are orthonormal, and we're going to show this later on. So here's the proposition. I claim that the characters of the reducible representations take the following form, where this A theta is basically the diagonal matrix which parameterizes a conjugacy class, and in particular, since characters are class functions, it's enough to compute the characters on the conjugacy classes. That's why we computed the conjugacy classes in the first place. So okay, so we have to compute the characters on the conjugacy classes. That is, we have this representation, and we want to compute the trace of the representation. But we see that if we activate the representation on fk, we get e to the theta n minus 2k fk. That means that the eigenvalues of the representation matrices related to the conjugacy classes are precisely e to the n minus 2k, where k goes from 0 to n. So the character is basically just the sum of the eigenvalues because the trace of the matrix is the sum of the eigenvalues, and we obtain the result which we claimed. This proof is rather trivial. Now, in the case of theta not being an integer multiple of 2 pi, we can say even more because we can compute this sum here. We can compute it because it's a geometric series. And I don't really want to spell out all the details in words. I think this is rather clear. You just sum up this geometric series and obtain the last equality, right? And this can also be rewritten as using cosines because these guys here, using the addition rule for the sinus function. And in particular, this shows that the characters are even, and moreover, it shows that they are 2 pi periodic because A theta is in particular 2 pi periodic. So they dance a subspace of the continuous class functions on SU2, which follows because we know that the continuous class functions on SU2 are 2 pi periodic even functions, and we know that cosine theta n and cosine theta, they do span this linear subspace of these guys. And this follows basically from Fourier analysis. So it's, if you want the theorem, it's called Fayer's approximation theorem. But I think this is rather clear. Okay, so we arrived at the Clebsch-Gordan decomposition, which is of particular importance in physics because this tells you how you add angular momenta or how you add spin in physics. So you always see this in physics, this thing spin 1/2 plus spin 1/2. But what does that mean? Well, spin 1/2 is basically just the reducible representation of SU2, and we want to see how tensor product representations decompose. And that's basically what this theorem tells us here. And to see this, we basically just start from computing the character on the tensor product representation. So this is the product of characters of VK and VL. So by the sum which we computed before, we have that we can rewrite this as this. So this is the character of K, and this is the character of L. Okay, and now what do we do? Now I just multiply out. So I have this multiplies the sum, and the second term multiplies the sum. But now I can use that this sum is even, because characters are in particular even, as we showed before. And therefore, by plugging this back into the sum and putting all the powers of I theta together, we have k plus 1 plus L minus 2m as desired. And minus, we have e to the minus I theta k plus 1 minus plus L minus 2m, because we pull out here an e to the minus I theta. And yeah, so this basically shows what we desired. because this using this formula basically is the character, the k plus l minus 2mth character evaluated in the matrix, which is on constant conjugacy classes. So the Clebsch-Gordan decomposition formula for the irreducible representations of SU2 reads as follows. It decomposes tensor product into direct sum of irreducibles. Yes. So now we want to prove, as I said, so remember there are some questions to be answered. We answered the first two questions, and we want to see whether they are all the irreducible representations, and want to see that the characters are orthonormal with respect to some inner product. But for the characters to be orthonormal, we still need a notion of integration of class functions on SU2. And now we have a theorem which gives us precisely what it means to integrate on class functions. And basically, this is just the push forward of the Haar measure. So we know that on SU2 the Haar measure exists. And now we push down the Haar measure, or push forward the Haar measure to the conjugacy classes, which are parametrized by real numbers between 0 and pi. So that's what we do here. Now we claim that this equality holds. Well, now we're going to prove this. So the proof goes as follows. We know that SU2 is a compact Lie group. So in particular, it admits a Haar measure. And we push or project this Haar measure to the space of conjugacy classes. But the conjugacy classes are 0 pi intervals, as we saw before. So we only need to determine a density f rho theta on 0 pi, which lets us integrate, for which this equality holds. And here f are continuous class functions in SU2. But as the theorem which we quoted before, so here, because they span a density in a subspace, we can approximate uniformly any continuous class function by linear combinations of characters. So in particular, it suffices to verify that the density rho, or well, we don't know which rho this is, but we're going to determine this from this condition, that this formula here holds for the characters. So we don't need arbitrary f, we only need the f to be a character of an irreducible representation. Yeah, and for the irreducible representations, we know that they are orthogonal by Schur's lemma, if you wish, or this can be seen easily. So the character, and in particular because the zeroth character is 1, then the inner product is basically 1 if the n is equal to 0, and otherwise it's 0 by orthonormality. Okay, so now we plug back our formula which we had for the characters. It's basically the sum of e to the I theta minus 2k. And we can read off because this has to hold. So this is 1 because the character of the zeroth irreducible representation is 1. So we don't have the sum. And for n greater than 0, we have this. This can be easily seen by induction, which I'm not proving here, but it's in my handout that these two conditions are equivalent to the condition given here. And now we want to find a rho theta which satisfies these two conditions. And we will choose rho theta in the way which is given here. So it's 2 over pi sine squared of theta. And I claim that this guy does the job. The computation of why this guy does the job I have in my handout, and you can check very easily by just plugging back for rho theta, plugging this back in here and in here, that all of these conditions are going to be satisfied. So in particular, we showed that the push forward of the Haar measure is the one which we desired. So now we have a notion of integration of class functions on SU2. And now given this integration, I want to give you some examples to see the full power of this integration formula. So the norm of the zeroth character of the character of the zeroth irreducible representation is simply 1 by just having this formula. It's very easy to check that this integral is 1. for n equals 1, we had the representation on c squared, but recall that the character was 2 cos theta. We computed that already before. And therefore, if we compute the square of the character, because that's what we're going to use in particular to integrate this over SU2, we have that this is 4 cos squared, and therefore by the formula which is given here, the norm of the character is basically 2 over pi, 4 cosine squared, sine squared theta by the virtue of this formula, right? So if we compute this integral, we once again obtain that this is 1 as we desired. And moreover, we can check orthogonality, namely that these two guys are orthogonal with respect to the measure which we gave. And yeah, this also follows from just computing an integral, which is not too deep. Okay, so we want to see something deeper. And something deeper is that we claimed that the tensor product representation of c squared with itself is basically not irreducible, right? Well, to see this, we first compute the character of this guy. The character is simply 4 cosine squared of theta. But now, given this, so given this, we computed the character, we can plug back in here, and we have to square this, so it's 16 cos to the 4 sine theta squared. And if we compute this integral, we see that this is 2. But if the norm of the character is not 1, in particular, this tells us that this is not an irreducible representation. So this shows that this is reducible, and moreover, if we compute the characters, I mean, we computed the characters of this guy already, but if we would compute the character of this guy as well, we would see that both characters are 1 and both of these are reducible. So we have shown in a different manner, or well, we have shown actually that it decomposes into direct sum of reducibles. And now I just want to show a really neat proof of the irreducibility of what we did before. So before we proved the irreducibility of the characters with a rather tedious and long proof. This is literally a one-liner having the integration formula on class functions, and I find this very neat. And actually this was only done in one reference which I found, so I really thought this is a really nice proof. That's why I put it in. So we see that we can compute the norm of the character of the nth irreducible representation by using the formula of integration which we found before. And here we basically just plug in what the character is. We computed it by the sum, so it was the sum, a geometric series, we computed it. Now we plug this back in here, we see that sine squared drops out, and if theta is not an integer multiple of 2 pi, which was required for this to hold, we obtain that this integral is 1. In particular, this shows that all of the pi and vn are reducible because their norm is 1. The character of their norms is no, the norm of their characters is 1, sorry. So this is a really neat proof, which would be a one-liner. Yeah. So now we come to the classification of these irreducible representations. Now I claim that the reducible representations Vn, pi n, which we gave here, are all the irreducible representations of SU2, which is a strong claim. So I gave you some irreducibles, and now we come to the fact of showing that these are all the guys. Well, we do this as follows. So we suppose that there exists an irreducible representation which is not isomorphic to these guys. If it's not isomorphic, then in particular it has a different character. But we know that the characters span a dense subspace. Therefore, psi, this character of the new representation W, can be approximated uniformly, in particular uniformly, by finite linear combinations of the characters of the irreducibles of Vn, but this contradicts the orthogonality relations. So yes, and that's the proof basically. Here I have a typo. I will correct this. This shouldn't be here. Okay, so now we obtain that the representations pi and vn, which we constructed, are all the irreducible representations of SU2. So in particular, in words, the irreducible representations of SU2 are the complex homogeneous polynomials in two variables of degree n. These are this guy's vn here. So these are all the irreducible representations of SU2. And in particular, because we have that by complete reducibility, so we know that for compact Lie groups we have compact reducibility. This means that every representation can be decomposed as a direct sum of irreducibles. This comes back basically to the existence of the Haar measure and unitary reducibility, but I mean I just call this result. And this shows a really important result in quantum mechanics. So in quantum mechanics, whenever we have an SO3 rotational symmetry, the Hilbert space, the infinite dimensional Hilbert space, which is the L2 of R, so or L2 of R3, so the space of square integrable functions on R3, square integrable in the Lebesgue sense, decomposes into an infinite direct sum of these VNs, which we constructed. And this is why the representations pi and v on are of particular importance in physics. And we call this spin representations. So physicists call this v and guys spin representations. And basically that's all there is to SU2. Now we move to SO3, which is the second part of the talk. SO3 as a Lie group is basically is again a matrix Lie group and consists only of rotation matrices of determinant 1, and here this should be identity. I'm sorry, I see this is a typo. Okay, and we know that SU2 is a double cover of SO3 by the isomorphism here. So SO3 is isomorphic to SU2 quotient out by identity minus identity, but the conjugacy classes are once again the same guys, and the class functions are in bijective correspondence to the guys we had before. But now we want to find the reducibles of SU2. And to find the reducibles of SU2, we see, because this group isomorphism, or well, because of this group isomorphism, it is enough to see where minus identity acts trivially on Vn. So we compute how minus identity acts. So the representation pi m related to the minus identity acts on the basis as fk in minus z1 minus z2. But by definition of who this fk was, namely the basis, we get that this is minus 1 to the power of k, minus 1 to the power n minus k on the basis. So basically we get that this is minus 1 to the power of n acting on the basis. So we conclude that in order for this action to be trivial, namely for this to be fk z1 z2, we must have that n is even. And if n is even, then in particular we have that the irreducible representations of SO3 are tuples of v2n and pi2n representations of SU2. And if we denote Vn by Wn by V2n, we conclude that all the reducible representations of SO3 are these tuples given here. So that's it, basically. Good. So now we want to think of the. So basically, that will be the end of my talk. But now I have like 3 more slides, which give a more natural geometric interpretation of these reducible representations. More natural in the sense that we also know that this SO3 acts is somehow related to Laplacian, right? So somehow related to Laplacian because we know that the Laplacian is rotational invariant on R3, for example, right? So we want to give a different representation space and to see how this is related to Laplacian. Well, so I define a space of complex homogeneous polynomials of degree n in 3 variables, and this is a vector space by pointwise multiplication and addition, and we denoted as Pn. So I denote this space as Pn. And we define representation of SO3 on this space as follows. So we have the representation map, which acts on an element of SO3. So this is going to be generally a map on Pn, but then I take an element of Pn and I evaluate it in x, y, z, and it's defined like this. Here also we would really have to check that this is indeed a representation, as we had to check before. That's done in my handout. I don't want to check it here because I think it's rather easy. But now we see that we can define the space of harmonic polynomials as a subspace of this guys, of this Pn. So this is a subspace of the complex homogeneous, of the real homogeneous polynomials in 3 variables of degree n. Basically, it's the kernel, it's Pn intersected with the kernel of the Laplacian. Good, so basically it's this, as I said it here. And now we have a lemma, which I'm not going to prove here. This is not too difficult to see, it's just some combinatorial argument, which is done in the handout. And using this lemma, we see that the representations Pn eta n, which I defined here, are reducible if n is greater or equal than 2. So the only reducible representation is P1, and that's a strong claim. And to see this, it simply follows from dimensional arguments. So from this lemma, we have that P0, dimension of P0 is 0. It's 1 times 2 divided by 2 is 1. And dimension of P1 is basically, so we have 1 plus 1 is 2, divided by 2 is 1, and times 3 is 3. Similarly for these 8s. And we know that for n greater or equals than 2, this Hn has lower dimension than Pn, so it's a vector subspace. But we also know that the Laplacian is rotationally invariant, so this Hn becomes a subrepresentation. But this is not trivial because this space Hn is not trivial per se. So this guy Pn is not trivial per se. And it's also not the whole space by dimensional arguments. So this finishes the proof that the Pn is reducible for all n greater or equal than 2. And now, finally, the last theorem we have to prove is that the representations, this pi n eta n, this representation space eta, Hn is isomorphic to Wn, which we provided before. And this basically follows from computing the characters. So if the representations of the if the characters of the representations agree, then they are isomorphic. So let us compute the character of the representation H1 and Hn. And we have seen before that this decomposes, Hn decomposes into a direct sum of Vn plus Vn minus 1. This is not too difficult to see. It's done in my handout. And here, basically, we just use that the character on the direct sum is the sum of the characters. And we use the formula which we had before for the characters. So this step is that it's the direct sum is the sum of character on the direct sum is the sum of the characters. This is basically just what the characters are. And now I just multiply out the brackets and use the addition rule full sign, and we arrive here by the addition rule of sign. And we use the formula for half angles, so this half cotangent